Hello, everyone, and welcome and thank you for joining the next webinar series. I am Aparna Deshmukh, Technical Director with Next, and I will be your moderator for today's session. So let's dive right into our webinar titled Application of Low Cement and High Dosage Admixtures for Concrete Mixtures. A PDF of this presentation can be found in the handout box. You can use the PDF to follow the presentation and take notes. You may use the question box to ask questions during the webinar, and our speaker will be happy to address them at the end of the presentation. For continuing education credit, attendance for the entire duration of today's live webinar will earn you a certificate of completion of 1 PDH. Your certificate will be available in ACI University under Certificates tab within 2 days. For those who cannot join us live, the on-demand recording will be made available about a week after the live presentation. ACI is an approved education provider for American Institute of Architects and the International Code Council, and this webinar has been approved for one learning unit. Please take note of our disclaimer on the screen for our next webinar series. So now let's get started with a short description of our today's webinar. The webinar will discuss practical ways to reduce CO2 emissions in concrete production by optimizing admixtures in sustainable mixtures with low water to cement ratio and cement content. It will explore their impact on concrete properties and present life cycle cost and CO2 emission analysis, offering new sustainable options for the industry. Our learning objectives for this webinar are as shown on the screen. Let's welcome and introduce our today's speaker, Dr. Mehdi Khanzadeh Muradlo. Dr. Mehdi Khanzadeh Muradlo is an assistant professor of civil engineering at Temple University with extensive experience in researching, designing, and specifying infrastructure materials. With over 50 publications focusing on durability and sustainability of concrete infrastructure, his research interests include novel sustainable infrastructure materials, construction technologies like 3D printing, durability and sustainability of concrete infrastructure, concrete pavements, service life prediction, and analytical imaging and microscopy techniques. Dr. Khanzadeh Muradlo has received numerous awards, including the PCA JP Gleason Research Fellowship, TRB Best Paper Award, ASTM International Emerging Professionals, GTech Best Paper Award, and Temple University Summer Research Award. And he is also actively involved in various ACI committees. Let's welcome him and listen to his presentation.
Hi everyone, welcome to the webinar. First, let me thank my PhD student Jafar for working on this project. As Aparna said, the goal is developing low cement, low water simulation, high admixture content mixtures, and optimizing those systems. So these are the outline for this presentation. We're going to have background. We'll discuss the motivation for the study, the objectives, and we'll discuss also the research approach we're taking on this project. Then we'll look at the impact on fresh properties by using these mixed designs, such as workability, setting time, air content. Then we will move to the performance criteria, the mechanical performance, the shrinkage, durability performance, and later on we'll show how this mixed design will impact on life cycle cost and environmental aspect. And at the end, we will rank our mixed design based on different combination of different criteria we are discussing here. So the motivation for this study, obviously, there's a big pushback in our industry to reduce the CO2 emission from cement and concrete production, and we are looking for different alternatives to do so. But the goal of this project, how we can do this by more simple and fast approach, basically. And if you look at the right image, we have different components of the our concrete mix, the basics, right? We have water, cement, aggregates, and air. So here we say if we reduce the water content and we reduce the cement content in our typical mix design, we can reduce the CO2 emission by 200 million tons annual if we reduce the cement content by 10%. And also if we reduce the water cement ratio from by 5%, we can reduce the again CO2 emission, the water usage by 100 million tons annually. So that was the big motivation behind this project, which is funded by Next. So we wanted to develop this low cement, low water cement ratio, and high admixture sustainable concrete mixtures. Probably say this is not a new approach. We've seen this, but the goal here is really to take a different approach to make it more practical and show overall how it's impact the different properties and, as I said, life cycle costs and environmental impact with the systematic research and show the benefit to the industry basically by doing this very comprehensive study. So these are the main objectives for this study. We want to optimize the system for this type of mixed design with low water cement ratio, low cement, and high admixture. We want to quantify impact on fresh and hardened properties, obviously. And then at the end, we want to see the impact on the initial cost, on the life cycle cost, and also the environmental impact. So here's very basic information on the approach we took. So I have this graph at the right side based on ACI 211, which is typically what we use for our mix design. So I'm saying if I am targeting 4-inch Islam for my mix design and the maximum aggregate size is 3/4 inches. And I'm assuming the typical water cement ratio I use for my mix design is 0.42. And for that 0.42, I'm showing basically the range of water content versus the cement content I can apply depending on that. The amount of the admixture I'm going to use for improve the workout is going to be different. And as I said, the goal is to reduce water cement ratio by 5%. So that's why I'm showing also 0.37 graph as well, based on, again, ACI 211 requirement. So the approach taken, we are here, we are assuming we are starting with a mixed design at this point with a 0.42 water cement ratio, and to give us that 4-inch slump with a certain high range water reducing admixture. The first thing we do is we first optimize this mixed design. By optimization, I mean the aggregate optimization. So we're going to have two mixed design at this point. One is the what we call as control mixed design. The other one is optimized control. So first, we're going to reduce the water cement ratio by 5%. That's what you are seeing. We are showing with this arrow, the blue arrow here, by 5%. So the difference here, we can move this direction. Basically, we can increase the cement content, but here we don't want to increase the cement content and say we reduce it by 10%. We want to keep the cement content the same, so that's why we are moving in this direction and reducing the water cement ratio to 0.37 while keeping the cement content exactly the same. So then we're going to have another mixed design at this point. We're going to call that low water cement ratio mixed design, or mixed design with 0.37 water cement ratio. And the next step, we're going to reduce the cement for this low water cement ratio system by 5% and by 10%. So we're going to have mix here with 5% reduction in the cement content and 10%, which is our goal as shown here with this next target orange star sign. So if we want to get really from here to this part of the graph, we're going to need a very effective high range water reducer in order to do this. So that's why we are using high range water reducer instead of normal range or mid range, because that's not going to work for this type of the system. So as I mentioned, we have to optimize our aggregate system for this purpose. So to do that, in our experiment, we use basically number 57 aggregate, number 8, and as well as our sand. So we, as a preliminary approach, we use this triangular curve, which gives us the combined gradation for concrete and aggregate. And we want to stay in this boundaries. These are the boundaries. You have to make sure you are staying within that boundary. So we change the proportion of aggregate, these three different sides of the aggregate, to make sure we stay in that range. And this is an example I am showing here. And again, the purpose here is to improve the packing density, reduce the void content. So we need less cement to fill those voids, or paste to fill those voids. Here are the mixed designs we have. So we have, as I said, control, optimized control at the initial point. The difference between those two, again, the optimized control, we optimize the aggregate system. And both of them has water binder of 0.42. Then we have low water cement ratio with the 0.37 water cement. Then we reduce cement by 5% for that mix and by 10% for that mix. So you see, when we move from this control to low water cement ratio, 10% low cement, the high range water reducer admixture content changes from 0.35% of the binder weight to 1.1 almost percent of the binder weight. This is almost 3 times increase in the high range water reducer content. Again, the target slam is 4 inch. We want to get to around that 4 inch slam to make sure the concrete is placeable. So these are some examples. So we have control, we have optimized control, and at the right side we have low water cement ratio, 10% low cement mix. So you see in control one, you see a little bit of bleeding in the system, but optimizing the aggregate, we get more cohesive mix design. So these are some metrics. I didn't want to bore you with a table. It's more how we move from the higher content to lower content. So cement for control one, 670.5 pound per cubic yard. So we reduce that by 10% for this sustainable mix to 603 pound per cubic yard. The water cement ratio, as I mentioned, we reduced by 5%. And then by doing so, the water content reduced from 281 pound to 223 pound. That's almost 21% reduction in the water content. So that's how we basically screened our different mixes we tested to get to this point, to get to our goal, which I discussed in the previous slide. This is again optimized gradation for different system. You see the control system number 57. It doesn't stay in that limit, so we have to change the proportion for those 3 aggregates to make sure we are within that boundary. The other fresh properties we looked at is the time of setting. We wanted to see how this high range water reducer with high dosage impacts the time of setting. So these are the values based on ASTM C403. You see the setup here, right? You are doing or measuring the initial setting and final setting time. So if you compare the result here, really the result is within plus minus 10-15 minutes for low cement or sustainable system compared to the control one. So we don't see much impact by using this high dosage admixture content. The other important factor as a fresh properties is the air content. As we know, when we are using a high dose of water reducing admixture with the air in train admixture, that can impact the quality of our air content. So it can reduce air content, kind of destabilize the air admixture. So we wanted to see how this new system we are developing is impacting that air content requirement. So to do that, we use the foam index test shown at the right side. We tested a different concentration of high-range water reducer, and we basically measured what is the air in train admixture content required to have a stable foam index, right? So as you can see, when we move from the control system to the that sustainable low cement 10% one, we are moving from 400 milliliter per 100 kilogram of cement to almost 1400. So that's basically proportion we are expecting an increase of the air in train admixture. So we use this preliminary data to design our air and train mixture. So the target for air and train mixtures was the 6.5% air content. We required 18 milliliter per 100 kilogram of the air and train admixture to get to that point for the control one. While for optimized one with the low water cement ratio 10% low cement, we required 45 milliliter per 100 grams. So that's almost 2.5 times more air and train admixture to get to that target air content. So other than the fresh properties, we looked at the hardened properties, starting with the compressive strengths. So we used the ASTM C39. We made the 4x8 cylinders. We cured them for different times in submerged lime water. So early ages, 3 days, 7 days, up to 90 days. So this is the data set you are seeing at the right side. So as we are expecting, when you are reducing the water cement ratio, we have to see higher strengths, right? That's what you are seeing here. But something I want to bold here is the performance of the low water cement ratio 10% reduced cement one, which shown here with purple. So as you can see, at early ages and long term, they perform superior compared to all other mixed design. And later on, we're going to discuss the main reason for here is reduction of void content or improving the packing density of the system in this type of mixers. So we see almost 30 to 50% improvement when we are comparing this mix design with the control mix designs. The other mechanical performance we tested was flexural strengths. We took these beams 4x4x16 inches, tested based on ASTM C293. And these are the results after 28 days curing and after 90 days curing. So you see again similar trend compared to compressive strengths. The optimized system with low cement is performing better than the other systems, and we see almost 35% increase in the modulus of the rupture after 90 days of the curing. We looked at the dry and shrinkage as a dimensional stability performance criteria. So the approach we took here, we cured our samples, our beams, for 7 days in wet condition. And after that period, we air cured the systems inside the environmental chamber at the controlled condition, 50% relative humidity and 23 degree of Celsius temperature for 32 weeks. So the results shown at the right side. So at the beginning, the initial wet stage, obviously the control system had more expansion. And we know because of the higher cement content. And when we look at the shrinkage, dry shrinkage data, we see pretty comparable data between our optimized mix design, low cement mix design, and control one. Even if we subtract the impact from that initial expansion, they perform maybe a little better than our control one. So overall, the shrinkage performance is comparable for the developed mixes, sustainable mixes, compared to the control one. We looked at the porosity of the system. We basically oven dried the system. We vacuum saturated. We submerged in the water to get the weights and then measure the porosity based on ASTM. And these are the results based on that. So we see the porosity for control number 57 is 12.3 percent, and it reduces to 9% for the low cement, low water cement ratio system. That's almost 22% lower porosity or dense microstructure for our optimized sustainable system. So you see, it's very correlated with what we discussed in the compressive and flexural strength experiments. So the impact from that higher packing density and improved microstructure. We looked at the mass transport properties to connect this to the durability performance of our mixed designs. The first one, we looked at the bulk electrical resistivity. The bulk electrical resistivity based on ASH.TP 119 as shown here. So we measured on 4x8 cylinders, so after curing time, and saturating the samples. So it basically measures what is the resistance of your sample or pore system to the current, right, the electrical current. And that indirectly measures how well it's going to resist, again, different deleterious material intrusion. So based on the test result, we have around 1.5 ohm meter for our control system, and that increases to 2.66 for our optimized low cement, low water cement ratio system. So that's almost 70% improvement in this bulk electrical resistivity measurement. So later on, we're going to discuss how we can use this electrical resistivity measurement to predict the formation factor. Basically, you are dividing these values by the pore solution resistivity, rho 0, and that will give you the formation factor, and you can connect this to the diffusion coefficient, which we can use to estimate the service life in the, for example, chloride environment. The other mass transport criteria we looked at is the water absorption based on ASTM 1585, as shown at the top right image. So after curing time, we seal the sample sites, and then from the bottom, we expose them to the water for about 10 to 14 days. And these are the results you are seeing based on the absorption. So obviously, when we are lowering the water cement ratio, we should expect lower absorption amount and lower absorption rate. But again, the other performance we are seeing for that 10% low cement one is performed better than any other mix, and the rate of absorption reduced by 40 to 120%. When we are considering the initial absorption rate and then as well as the secondary one. So this means the permeability of the system, considering the water absorption and the bulk electrical resistivity, improves when we are using this optimized system, and that correlates to the lower risk when it's exposed to the freestyle environment or chloride-induced corrosion. So the other criteria we looked at is the life cycle cost. So we want to see what are the life cycle costs and what is the impact by use of high admixture, low cement mixtures compared to the control one, the typical one we use in the industry. So this is from literature. Basically, you can have different criterias or consider different criterias in the LCCA model. So material cost, construction cost, maintenance, repair, and end-of-life cost. So most of these criteria are consistent between our mixed designs. The main ones that are varying here is the material cost, because we are changing the material content or proportions, and also the service life, the performance, how that performance correlate to the repair and maintenance cycles, and obviously the life cycle cost. So those are the main criteria we considered here in our analysis. So as shown here, we accounted for the difference in the initial cost by changes in the mix proportion, the maintenance cost, and the service life. So the way we compare different mix design, one by taking a 1 cubic yard of the concrete for each of those mixes and comparing the life cycle cost. And the other example we're going to show, we took this bridge deck section around 10,000 square foot, and with this thickness and cover depth, and we showed what are the life cycle costs for that particular section of the bridge, which is located in the Philadelphia region. So the initial material cost, we took this initial cost from literature and different sources, and based on that initial raw material cost, we calculated what are the initial costs for different mix design per cubic yard. So that's what you are seeing in this bottom table. Basically, for control one is around $144 per cubic yard, and it increases to $160 for the low var cement, 10% low cement. And the reason for that, because we are using a higher dosage of the admixture. The net present worth analysis, that's the approach we took to do our life cycle cost analysis. For derivative consideration, because it's important to consider this in the life cycle analysis, we assume that our main derivative factor is going to be corrosion due to the chloride intrusion. So to calculate the service life in that environment, we use the Live 365 software. It's open access software, which uses the fixed second law to predict what is the basically when the concentration of the chloride at the rebar level is going to reach the critical level, which we assume is 0.05% of the concrete weight. For surface chloride buildup, we took the database for the highway bridge in Philadelphia, as I mentioned. For diffusion coefficient, we didn't get the values from the software. We put the values based on our experiments. As I mentioned previously, the bulk electrical resistivity measurement, we calculated the formation factor, and then we correlated based on first principle, we correlated that to the diffusion coefficient, which then we can use fixed second law to predict how long it's going to take to get to that level. These are results for derivative concentration. So you see different concrete mixes, the service life predicted. So for control one is around 30 years, and it increases to around 53 years for low var cement ratio system, and it increases to 66 years to for our optimized sustainable low cement system. So that's almost 117% increase when you are comparing that system with the control system improvement, the derivative. The maintenance and repair, we assumed we're gonna repair 10% of the area for that bridge deck, and that's the assumption for the cost per square foot for the repair. The long-term inflation rate, we assume 3.28%, the discount rate 3%. The analysis period, we assume it's 100 years, starting from 221. So based on this assumption, when your service life is basically you reach to that service life we discussed here, you're going to start the repair every 20 years. So that's the assumption we made in our analysis. So based on what we discussed, this is the life cycle cost for 1 cubic yard of the concrete for different mixes we developed. So starting with the control one, around $1,088 for one per cubic yard, and it reduces to $774 for our low cement, low var cement ratio system. So that's almost 29% lower life cycle cost when you're comparing that sustainable system with the control system. This is another way we can show the life cycle cost, the cumulative present value. As I mentioned, this is where the service life ends, right, for that particular mix design after 30 years for control ones, and then you start the repair process. So you repair it, and then after 20 years, another repair, and so on and so forth, up to that 100 years service cycle. For the other mix designs, the low water cement, low cement one, you are starting repair after 50 or 66 years. So that's why your life cycle cost gets reduced. So that's the impact you are seeing from the better performance criteria. This is a summary table based on different mix design for that 10,000 square foot bridge deck. So you see different mix design, you see the input parameters, the assumption we made for the steel type, the percentage of the steel. Again, we kept it consistent to make sure that's not impacting our analysis here. That's the predicted diffusion coefficient at 28 days. The initiation of the corrosion for different mix design, you see it's 25 years for control and increases to 60 years for the our sustainable system. The propagation period for the corrosion, we assume is 6 years for all of the mix designs. And based on that, the service life, and as I said, these are the life cycle costs for that section of the bridge deck. Again, almost 29% lower life cycle costs when you are using a low water cement ratio, 10% low cement compared to the control mix. From the sustainability perspective, we want to see what is the real impact from use of this mix design on some of the sustainability indicators. So to do that, we've done life cycle assessment analysis. So we use the cradle to grave approach here. We assume the transportation cost or the impact is about the same for all the mix design we have, and these are the 4 different stages of the life cycle analysis or assessment you have to consider. For this study, I'm going to be short and present a very summarized version of what we have. So we assume the functional unit is 1 cubic yard of the concrete. So that's the unit we take to compare the environmental impact. We have to do comprehensive data collection for raw materials, the energy cost associated, and other criteria. So to do that, we, especially for raw materials in this study, the high range water reducer, the OPC cement, we collected data from literature, from EcoInvent database, US life cycle inventory, and so on, to make sure we have a comprehensive data collection in this stage. To look at the impact assessment, the life cycle impact assessment, we use this impact 2002 plus method. So as shown at the left side, at the right side, there's 4 damage categories here based on this method: human health, ecosystem quality, climate change, and resources. And there are 17 different midpoint categories which are listed here. So you can take a different midpoint categories for your assessment depending on importance of each of these in your project. For the purpose of this project, we took 4 different midpoint categories which are highlighted here. One is ozone layer depletion, the ecotoxicity, and global warming, as well as the non-renewable energy. So the way we pick this midpoint categories to make sure they are representing different damage categories we have at the right side. These are results from the life cycle assessment. So you see, when we move from the control mix to the sustainable mix, which is low water cement 10%, that's what we call, except the ozone layer depletion, the other 3 criteria or midpoint categories, we see reduction, right? So which is a good thing. But regarding the ozone layer depletion, we see increase when we move from control to the low water cement ratio system. And the big driver for this is emission of this CFCs from the high range water reducer, because we are increasing the dosage, so that contributes more to CFCs, and that's why you are seeing increase here. But the most common indicator we use in our industry is the CO2 emission reduction. So if we compare the control system to the low water cement, low cement system, if we move from that control system to that what we call sustainable system, there's an 8.7% reduction in CO2 emission, which I mentioned here. Okay, so we discussed different criteria, right? The mechanical performance, the derivative performance, the life cycle cost, and the sustainability aspect of our mix design. So at the end, we wanted to really rank based on different criteria we have, what is the ranking for different mix design we developed. So to do that, we took this multi-criteria performance evaluation approach using this simple additive weighing formula shown at the right side. So what you are doing here, you're basically selecting different criteria you want to include in this assessment. So we took 4 different criteria. One is combined strengths to have the impact from the mechanical performance. The second one is the durability. So we considered the service life data here. The third one was the sustainability. So the 4 categories we discussed in the previous slide, we consider the combined effect from those 4. And lastly, life cycle costs. We take into consideration how the life cycle going to impact in overall year. So the other important factor here is the different weights you are putting on this different indicator. So you are dividing that 100% to different criteria we discussed. So depending on the importance, you can put a different weight. But in this project, we assume the weights are the equal, and for each of the criteria we are considering is 25% out of that 100%. So again, we have environmental aspect, we have combined strengths, we have life cycle costs, and we have service life as a 4 different criteria we are taking into account for ranking of different mix design, and we are assuming they have equal weight. So these are the ranking based on the criteria we discussed and based on calculating or using that equation I showed. So here's the table. The rank 1 is basically low water cement ratio, 10% low cement 1. The total score for that mix is 1. So that's the best mix based on our ranking and 4 different criteria I discussed. The rank number 2 goes to low water cement, 5% low cement 1. And rank 5, the last one goes to the control 1. Basically, when you move from rank 1 to rank 5, which is control 1, you see almost 30% improvement in the performance or in the ranking performance we are considering here. So based on what we discussed so far, so these are some conclusions we can derive based on the data we have. So the low water cement ratio, low cement system with 10% reduction in the cement require 3 times a higher high range water reducer content to satisfy the workability requirement, which is the slump value. The setting time, impact on the setting time was not much. The data was comparable. For air intake admixture, the required air intake admixture content increased by 2.5 to achieve the target air content. The developed sustainable low cement system improved the mechanical performance by almost 30 to 50%. When we look at the shrinkage drying performance, it was comparable to data between the developed optimized systems and the control ones. When we look at the permeability mass transport criteria, we saw the improvement by using this low cement, low water cement ratio optimized system which again, that translates to improvement in the durability in our structure in a harsh environment. And if you remember, based on our prediction, we saw almost 117% increase in the service life when your concrete is exposed to the chloride-induced corrosion. The concrete mix with 10% reduction in cement has the lowest life cycle cost based on our calculation, almost 29% lower. Based on life cycle assessment, we see reduction in the CO2 emission by 8.7% when you are comparing to the control systems. And based on our ranking, the 10% reduced cement, low bar cement ratio, mixed design ranked first and performs 30% better than the control. So the general conclusion can be here based on what we discussed and the data we gathered here. The developed low cement system, optimized system, can be an immediate solution to reduce the CO2 emission from cement and concrete production. In other words, we don't need to look for a magic in our industry to reduce the CO2 emission and make our system more sustainable. We can optimize our system, make sure it's placeable, and also performing better and has the lower life cycle costs. Regarding the initial costs, maybe if we consider the incentives from the reduced CO2 emission, it can compensate part of that initial cost increase in this developed systems. These are the references we use this for this study. Thank you again for your attention. And also, again, I would like to thank the NEX for supporting this project. This is my contact information. Please feel free to send me email and contact me if you need further information related to this project. With that, I think we are open for questions.
Great. Thank you, Mehdi. Thank you so much for the outstanding presentation. I think it just included all the crucial points which we really needed to understand. So with that, let's move to our question and answer session. We have few questions here. So our first question is from a practical standpoint, how do you get your local ready-mix suppliers to provide the optimized aggregate grading that is required to achieve the improved performance?
So actually, we are working with one of our local ready-mix plant. So they have access to number 8, and they are using number 57 every day. And actually, for some of the specialty mix design, they are optimizing their system. But they think this optimized system is less, let's say, workable, or the placeability is the key there. And by doing this experiment, by optimizing your system and increase a little bit in your water cement ratio, we show that it works. It's a placeable system, and we can apply it for different applications. So that's what we are trying to really convey to the industry. Maybe you see a little increase in the cost, but overall, that's going to pay off in long term.
Great. Our next question is regarding the admixture dosage. So how did you select your admixture dosage, and what was the logic behind it on the top of manufacturer recommendations?
Sure. So we tested different admixture from different resources. The one I showed is just the one example, which shows maybe a little better performance compared to other resources. But the way we optimized aggregate, we started with certain recommended values, and then we basically adjusted admixture to get to that slump value. So as I said, the screening method was more the workability. So in order to accept the mix design and get to that point that admixture is acceptable, dosage is acceptable, we looked at the workability. But obviously, also we worked a little bit on the optimized gradation. That goes hand to hand. So we may needed to a little change the proportion of our aggregate because the required paste quote the aggregate is can impact your workability. But those two criteria is how we basically adjusted our mix design to get to that optimum level.
So did you go beyond the recommendations from the manufacturers, or it is
Yeah.
within?
I believe we went beyond that.
Okay, okay, great. Our next question is, how many different type of admixtures did you use? Water reducers, air entrainers, and corrosion inhibitors.
For high range water reducer, we tested, I believe, 4 to 5 different admixture from different companies. For air intake admixture, we limited to just one admixture due to the scope of the project. But I think the approach can be applied to any other admixture,
Mhm.
air intake admixture. The other one was the corrosion inhibitor. We didn't use any
Yeah.
corrosion inhibitor.
hmm I think, yeah, the question might be, I'm not sure. So maybe in one mixture, how many admixtures did you use? That could be the question. Like, uh,
So if the mix design is for not, let's say, freestyle environment, you don't need to use air intake admixture. In
mhm,
that case, we just use one type of high range water reducer. We didn't need to combine
mhm.
multiple admixture. If you are using for basically freestyle environment, cold environment, then you are combining air and train admixture with high range water reducer we have.
Okay, great. Our next question is, are the results valid for type IL and LC3 cement as well?
Um, Probably I'm going to say not because we haven't tested them, but the
Mhm,
approach can be applied for any other mixes. Maybe if you use LC3, you have calcine clay, the values are going to be different because calcine clay typically requires uh, higher admixture content. So, but approach can be applied easily for any other type of system.
Yeah, on the similar ground, the other question was, did the testing utilize an OPC or PLC?
OPC,
Okay,
type 1 OPC.
great. Our next question is, in your ranking system, so it should be regarding LCCA. In your ranking system, do all your four criteria have the same weight, and why?
Yes, we put the same weight. It's arbitrary. You can change it, but we thought just for sake of example, just let's keep it the same. We didn't want to have a bias to one factor compared to other one. But
hmm
obviously, depending on your um, project and the importance of the any of those criteria, you can change that weight.
Okay, great. I think we have one last question. How does this mixed design setup and finish? We have seen high dose HRWR mixes get a jello effect, where the lower section of a slab on grade sets at a slower rate than the top, creating great difficulty achieving levelness and flatness. Have these mixes been evaluated by concrete contractors?
Not yet. So that's what we are hoping uh, to convince the contractor to start at least try some of our mixes and see what is the if there's any implication in the field and if there's any challenge related to that. That's the next level we are considering here.
But did you, so the one part of this question was, does the mixed design setup and finish, you did setting, check
Yeah,
the fresh properties, right? So do you
yeah.
think it does behave something different, like showing jello effect or something?
Not really. We didn't see much difference. So as I showed in the pictures, actually it's improves the cohesiveness of our mixes.
Mm-hmm.
And the time of setting, we have around 10 to 15 minutes plus minus difference that initial setting, final setting. Um, so the concrete samples we made, the maximum thickness is 4 inches. So I don't know what is the thickness of the slab they are discussing.
Mm-hmm. Yeah,
That
that's
may impact it, definitely. I'm not sure about that, but
yeah. So, sorry, but we have two questions more. So, other than the two admixtures that were, is there a shelf life concern for the various admixtures used in the study?
um, I mean, we acquired it from different companies,
Mm-hmm.
and we really didn't worry about that shelf life.
Yeah.
Um, I don't think that's going to be a problem because these are typical admixtures
Mm-hmm.
they are applying in the industry currently. So it's not really new admixture. It's because we want to use the common ones so people have access to those admixtures.
Yeah. Our last question is, how do we get design engineers to specify low cement content with high dosage water reducing admixture concrete mixtures that have favorable life cycle assessment compared with the traditional concrete mixtures without water reducing admixtures?
Well, that's a good question. I think part of it is obviously the specification, right? We have
Mm-hmm.
to start. So that's one thing we want to work with some of the ACI committees, hopefully, to get some of this data in their different specs, different document they have to show the promise. And obviously, the other part is going to be how comfortable the contractors are to apply this type of the system. I think one part is really the working on the specification. The other part is working with the, our industry to start applying this type of system.
Great. Great. Thank you so much for answering all the questions. I think by this, we are at the end of our question answer session. You can see my screen, right? Okay. So,
Yeah.
yeah, so before we go, we have some few announcements. Um, let's see. So next is sponsoring FRPRCS 16 symposium that will take place on March 23rd and 24th in New Orleans during ACI Spring Convention. This symposium will emphasize on new frontiers of FRP research and experimental, analytical and numerical validations of using FRP composites. It will also provide insights needed for improving existing guidelines and developing design codes. So this is open to all ACI convention attendees. So for more details, please visit ACI 2024 Spring Convention page, that is current convention, and go to session and event option, and you will get the details. Also, you can visit frprcs16.com website where they have the full program schedule. So I hope you would be able to attend the this event. And this is a list of our upcoming webinars at ACI University. So please visit aciuniversity.com and to register for the upcoming webinars. And again, thank you all for joining today's webinar. We look forward to having you with us again in our next webinar. Have a good rest of the day. Thank you.